Okay, welcome to part C. This will be the final part within module 3. It's also another long one. So definitely recharge your coffee as it will take a while to get through. Again, we do have embedded videos to save my voice because it is such a long chapter. So in this one, we'll be covering IP services, network security best practices, and a little bit of introduction into cryptographic processes, so protecting our information in transit. So first section is IP services. So we'll be looking at vulnerabilities to do with IP. So ARP is a inbuilt protocol that, if you cast your mind back, is there to provide you with address resolution. So this is there to map layer 3 and layer 2 addressing together. And this can also be used to claim ownership of an address that isn't yours. So basically what they do is they can send incorrect information back and corrupt your ARP tables on a device, and this allows them to launch a man-in-the-middle type of attack by redirecting to the incorrect addresses used within the services. So let's just remember what ARP does. So PCA requires the MAC address of the default gateway, which is router 1, and requests the MAC address of the gateway's IP address. Router 1 updates its ARP cache with the IP and MAC address from PCA and replies with the information to PCA that it's requested. The threat sends 2 spoof replies using MAC address indicated within the information of the original request. PCA now updates the ARP cache with the default gateway, now pointing to the threat actor. Okay, router 1 now updates its ARP cache with the information pointing to the threat actor. So this is how we corrupt the ARP tables and then redirect traffic to perform man-in-the-middle. So let's have our voice in the box go through this process for us.
Welcome to ARP Spoofing. This is going to be great. To get started, I've got PC1 here that wants to communicate to the web server. PC1 is on the 192.168.1.0 network. The web server is on the 2.0 network. For PC1 to get there, we've got to make our way through this router, which is R1. R1 is acting as the default gateway of our network with IP address 192.168.1.254. R1 has the MAC address ending in 9902. So PC1 is going to have to communicate with this router in order to make its way to the web server and get a response back. Now, quick recap of how ARP works. In order for PC1 to get to the web server, it needs to know the MAC address of its default gateway. So let me open up PC1, go to my command prompt, and we're going to do an ipconfig /all. And with our ipconfig /all, we'll see that PC1 has its MAC address of B0EE. It's got an IP address of 1.10, and it knows the default gateway IP address. It knows the router is 192.168.1.254. However, if I take a look at my ARP cache with an ARP -A, there's nothing in there. It doesn't know the MAC address yet for router R1. So if I were to send out a message, like maybe I want to ping 192.168 2.100, that remote web server, the first ping is going to fail. And that's because my PC1 is resolving with a who is 1.254. And by the time that ARP resolution happens, the first ICMP ping message timed out. But that's okay. The other three were successful. And now when I check out my ARP cache for an ARP -A, we can see that my default gateway 1.254 is known as MAC address 9902. Now this is awesome. Lab is complete. Well, what if it's not complete? Well, just to kick it off, one last thing to try out here. I'm going to open a web browser on PC1. And now that we have layer 3 reachability to that server, I'm going to go and use port 80 of TCP and hit that server at its IP address. And we have connectivity on port 80 using TCP. So this is great. Well, when does that threat actor come into play? Well, how about now? My threat actor, I'll open it up and go to my command prompt, has an IP address and MAC address already. And this is just a normal user on the network that has too much time on their hands, maybe. This user has a MAC address of 2088. It has an IP address of 1.20. And it also understands that the default gateway is 1.254. But what if this threat actor wanted to be a man in the middle? Well, we can make it happen. I'm going to go ahead and go over to my router R1, and I'm going to go into my interface that's connected to this 1.0 network. I'm going to grab that MAC address. And then we're going to go back to that threat actor machine. Don't worry, threat actor, we're going to give you a gift. On the threat actor's interface, we're going to change its MAC address to spoof the MAC address of the default gateway. Now that it has the MAC address of the default gateway, let's have some fun. I would send a gratuitous ARP over to PC1. Because I don't have the ability to do that here in Packet Tracer, how about we send a constant ping? And this constant ping is going to be talking with the IP address of PC1. And you know what? Who's the source? Us. Us, threat actor machine, now with this spoofed MAC address, which would be the default gateway. And I want to show you something. On PC1, let's take a look at our ARP cache now. ARP -A. We see that 192.168.1.20, hey, check it out, has that MAC address of the default gateway. And also, let's go over to the switch, our Cisco networking switch. Let's verify our MAC address table. So MAC address table, dynamic. And let's take a look at the MAC address learned off of port 2. And check it out. Off of port 2 is the MAC address now of the default gateway. So now what happens when PC1, which we're going back to right now, tries to browse the web? Open our web server up. Let's go back to 192.168.2.100. Enter. And it's just timing out. You see there's no activity lights moving here at the top regarding this traffic. It's a timeout. But now comes the fun part. If our threat actor is running a type of analyzer for traffic, such as this network sniffer sitting here right outside, I can go into and click on one of those messages, and I can actually scroll through and read through the headers, as well as even be able to read through the data fields of the traffic. And what we can see here is the source IP was 1.10. That was PC1. The destination IP was meant to go to 2.100. Well, then how was it switched over to the threat actor? Because the switch thinks that off of port 02 is MAC address 9902. The spoof was successful. If I scroll down, you can see here in layer 4 info that this thing was targeting port 80, destination port 80, source port 1026. Man-in-the-middle attack, successful. And if we had better threat actor software, we could really capture this data and at the same time be sending it onwards to the default gateway ourselves, acting like everything is just fine, using a beautiful.
All right, so from there, you see how easy it is to use that vulnerability to redirect traffic within your network. Next one is the domain name service, and this one is used to give us an IP address for a domain name. Now, this allows us to use names that us humans can remember rather than a whole bunch of numbers. So what can be used against us? Well, we can have open resolver, stealth attacks, domain shadowing, tunneling. So there's quite a few things that can occur that is inbuilt into this protocol. So we can poison the cache we can use the amplification and reflection, which we saw earlier, and we can chew up resources within the systems. Now, again, we'll have a video, a couple of slides down, I believe. So, if not, press pause, read the slide. Otherwise, you can go through it in more detail in the curriculum, obviously. So, fast flux is a technique where we basically hide the phishing and malware delivery behind this. And we continuously change the IP addresses, thus hiding the source of the attack. Double IP flux uses the same thing, but it's also changing the mappings, so it makes it harder to track the source. Last one there is domain name generation algorithm. These randomly generate domain names and points them towards a command and control server, which can then redirect legitimate traffic. Shattering attacks allows us to gather domain account credentials and then create multiple subdomains during an attack, and using these subdomains as malicious servers that we can launch other attacks from, and the source looks like it's coming from a legitimate server. Tunneling allows us to redirect traffic using the DNS queries. So we must filter and inspect DNS traffic for us to detect and mitigate this type of activity. Now, one of the things you can do is only allow your information from a certain set of addresses. The problem with that is that, as you saw earlier, IP addresses and MAC addresses can be spoofed. So mitigation is problematic. DHCP is used throughout every network basically, and it's broadcast, and it relies on our neighbour's dog barking to reply and give us the offer. We then accept this offer and get an acknowledgement that it is now ours to use. Now, within these spoofing attacks, we can insert a rogue server and alter the information that our devices receive via intercepting and using a different server. So basically we get an invalid gateway address or something that allows them to perform man-in-the-middle attacks. We can redirect them to an incorrect DNS server, which then redirects them to malicious websites, and we perform attacks from there. Invalid IP addresses, invalid default information can be created to perform denial of service attacks, basically turning our machines into those little lovely zombies. So basically, when we're trying to do legitimate tasks, we're actually launching attacks against a target on behalf of the threat actor. So let's assume that they successfully installed and got the rogue DHCP server up and running. When the broadcast is made for the discovery request, it will receive messages from both the valid and rogue DHCP server. Now, the way it works is generally the closest server will respond faster. So this potentially enables the rogue to get its offer in first, and then it will control the information that that new host is getting. Okay? Because the host, when it boots up and does this discovery, doesn't know that it's not a valid server. So let's have a look at best practices. So confidentiality, availability, and integrity. These are the hallmarks of protecting ourselves. So confidentiality means only authorized people, individuals, processes can gain access to the information. Integrity is the way we protect the data from alteration, and availability. This means the information is available to authorized users as and when they need it. So one of the things we need to look at is defense in depth. It's no longer valid just to protect our edge of our network from the outside. We need multiple checks and balances throughout the network. So we need to layer all of our approaches and our mitigation techniques and monitoring. We have to have it everywhere within the network, all on the various segments, and looking for abnormal activity. Remember, only a relatively small portion of threats come directly from outside. Most of these threats are from compromised systems internally. So we need this multi-layered approach to capture the threats evolving within our network rather than relying on our boundaries to do it for us. So what devices allow us to do this? VPNs allows us to encrypt communication between devices. Our adaptive security appliances allow us to do different firewalls and do different functionalities within a single device a lot of times. Intrusion prevention systems, or the older intrusion detection systems, the difference between them: the detection system will only set off an alarm. A prevention system will alarm and take an action. So use the newer technology, it will help us better. Then we have ESAs and WSAs, so this is protecting our communications through the web servers and things like that. And AAA service, so this is a authentication server that provides authentication, authorization, and auditing of devices within the network. Then you go around and actually harden all your intermediate devices, such as your routers and switches, so that it becomes harder to gain access to them without authorization. And using the various methods, we can secure our communication paths. So what is a firewall? Firewall is basically a set of rules that implement a security policy on what traffic is allowed to come through that device. So it's a big filter. So in here we have a set of statements that allows traffic from the external addresses to the web server. It allows FTP to the server, SMTP to the server, and traffic to the IMAP server. So it basically denies everything else. So the rule of thumb for security devices like this is denial and then open the doors for the things you want to allow as a general rule of thumb. Intrusion prevention systems will use a library just like your antivirus. They have a library which is basically a set of conditions that it looks for. These can be updated on a regular basis, and they can then be very adaptive to new threats as they evolve throughout time. They detect patterns within the traffic using the signatures, which are the rules, and they will take a action based on the match of the pattern. So it has a set of conditions that must be met for it to be considered a threat, and then against that threat level you'll have some actions listed against it, such as, okay, trigger the alarm but do not stop it, trigger the alarm, block the traffic. There's many different rules that can be applied. So as you can see here, this one is a rule that says drop the packet. So our malicious actor sends a threat and the traffic's intercepted, evaluated via the IPS, and it matches a policy. So what it does is it sends a log message saying it's had a positive match. So this is the alarm, and then it's dropped the malicious packet so it can no longer be used. So within the realm of other things that occur is email security appliances that are designed to monitor SMTP traffic, and then we've got the web security appliance, which is there to monitor web-based traffic, and those two combined will provide secure communications in a lot of times. Now again, we have rules to be applied, and this allows us to have complete control over what gains access to the internet, and we can blacklist specific sites, we can filter, we can do live malware scanning, we can filter based on applications, we can allow encryption and decryption of traffic. It is very good tools to help protect our information. So cryptography is a whole course on itself, but here's the voice in the box.
Hello everyone, we are here to secure our communications. What that means, our organizations need to provide security for data that is stored on our machines as well as moving across network links. Well, to get started, we're not just going to start sending data around. Let's start first by making sure our data is the correct data. For example, on my desktop, I have this folder titled Important. And in this important folder, I've got these 6 files. Now, how do I make sure that these 6 files that have data inside them have not been maliciously altered or changed since I last used them? Well, that's called hashing. It's part of data integrity. What I can do is open up another program, for example, this one, Quick Hash, and I can go to that directory, and I can select the directory of important where all those files are in. If I go into important and click select, this program is going to hash all of those files. And due to the exact bits of data in each file, you will get a specific hash value that correlates to that file. But what would it look like if one of those files had been altered? How could I check that? For example, maybe financial records or employee passwords. Is I can go to an individual file and select it in this hash program. And how about we do employee passwords? And it will give me a hash output. Now what I can do is I can go to this file of employee passwords and I'll change it by 1 character. To change it by 1 character in employee passwords, how about Dragon 0 becomes Dragon 00 with 2 zeros? What I'll do is save the file, employee passwords. We're going to go back into that hashing program, and we're going to take a look at how this hash is about to change. Before it was 6.5 in the beginning, 4.6.3 at the end. Let's go to that employee password file one more time. Take a look at this. It is completely different. And to compare it, I'm going to paste in here what I expected the hash to be, what it should have been if it didn't change. And the program says this does not match the previous hash. If you compare those two, they are completely different, just by adding on an extra 0. So this is data integrity using hashing. What I look at now next is the idea of encryption. So what we want to verify here is that when we move our files from one place to another, it's nice to know that they haven't been modified using integrity and hashing, but it's also nice to know that they haven't been intercepted and viewed. So we need to encrypt these files. Now to do this, I'm going to use an open source program known as 7-zip. Now with 7-zip, I have it looking at that directory marked as important, and I will take a couple files. How about employee passwords and employee records? I'll take these two, I'm going to right click on them, and I'm going to put them in an archive with 7-zip. And this is going to give me some options. The option first is to name the file. And I'm just going to name this file as secure.7zip. And for the password, which is going to be a symmetric encryption password, I'm going to use super secure. And this is going to encrypt these files inside of this new file known as secure.7z. And in order for people to decrypt and view these files, they'll have to have the encryption password of super secure. Since it's the same password used to encrypt and decrypt, that's known as symmetric encryption. I'll click OK, and we're going to encrypt those 2 files. First one's done, and the second one's done. So I've got this new file, secure.7z. And in order to gain access to it and view the confidential data inside of it, I have to right-click, go to 7-zip, and I'd say extract the secure. From there, I get my password pop-up in order to decrypt the contents, and that will be the password, again, of super secure. You can see it, and I'll click OK. From there, it's going to open up a new directory right here. It's decrypted those files, and now those files are right here. If I wanted to now, I can verify these files have not been altered in transit, and that would be by using my hashing program for data integrity. So cryptography here is going to provide you data integrity, origin authentication, making sure a message is not a forgery, and it actually comes who it said it came from. Data confidentiality, which is our encryption, and making sure that if data is intercepted, it can't be deciphered. And also non-repudiation, where it guarantees that the sender cannot refute the validity of their message. They are the one who originally sent it, and they have signed off on it.
All right. So as you can see, it's very important that we secure our information for multiple ways, and using the various hashing algorithms and systems, we can protect them from changes. We can also protect the information in transit using this system. So wherever we have information stored digitally, we can use systems to protect that information. So the integrity, the authentication, confidentiality, all of this is able to be done manually as well as automatically. Remember, anything we can do manually, we can automate. So the integrity, as you saw, is making sure that nothing is changed in the information between having it sent and received. And if you've downloaded operating systems and that down from the web, you'll notice that most of the sites will have the file, and next to the file they'll have the hash value for that file. So once you've downloaded it, you can then use the same hashing algorithm to compare what you've downloaded is actually the original integrated device. So in the example here, we've had a paycheck altered. So originally it was pay Alex $100, now it's pay Jeremy $1,000, and the hashing you can see is quite different as the information has changed, and this means the information has been invalidated and they will not take action on it. There's lots of different hashing algorithms out there. The three best well-known is MD5, SHA, and SHA-2. Now, these have improved over time, just like every other technology out there, and what we now do is basically increase the bits used to help encrypt the system. The larger the bit value on the SHA means it will be harder to break. Okay, so SHA was originally 160 bits, MD5 was 128 bit, SHA-2 ranges from 224 bit up to 512 bit, and AES and other encryption methods use even more bits to help encrypt things. So authentication. With this, we take the original source message, add our key, put it through the hashing algorithm, and we have a fingerprint for authentication. So this is a keyed hash message authentication code, HMAC, and we use this to protect not just the message, but to prove it came from our source. So with confidentiality and encryption, there is two methods. One is symmetrical and the other one's asymmetrical. What's the difference? Well, symmetrical, as you saw in the video, uses the same key, both to encrypt and decrypt the data. Asymmetrical uses different keys. These are known as private and public keys. Now, the idea behind asymmetrical is you have a private key that only you know. You give your public key to people you want to use communication services with, and they use that key to decrypt your message so they can view it. When they reply to you, they use your public key, and you can decrypt the message using your private key. So it's a pair of keys that are different but can unlock the message. So symmetric encryption, here we go. Nice little graphic down the bottom there, allows us to encrypt the message so it doesn't look like anything, and then when it's received at the other end, they use the same key to decrypt it and get back to the original message. Some of the encryption methods used is DES, triple DES, AES, SEAL, and RC. Now, all of these use different ways of jumbling up the characters of the original message and securing the information. Basically, I went through what the lovely asymmetric encryption does, so I'll just skip over that. So what we do with asymmetric is we tend to want to use this within IPsec VPNs, and one of the things we do is we use Internet Key Exchange, which is IKE, in conjunction with other functions to exchange keys in a secure manner. Other things we can now use are secure socket layer, secure shell, and pretty good privacy. These all allow communication in an asymmetric fashion. Now, because it is asymmetric, it's not as fast as symmetric algorithms. Okay, so they need to compute larger numbers and use specific discrete algorithms, and this takes more time. So because of this, it's typically used for low volume traffic, such as signatures and key exchanges. And then we come to a different set of algorithms to protect our data. So we've got Diffie-Hellman with key sizes between 512 to 4096. Then we've got DSS, DSA, RSA, and Gamma elliptical curve techniques. That's a new one for me. I haven't actually used that one before. So these, okay, for example, quite often when I used to set up VPNs for site to sites, I would use IKE and Diffie-Hellman to set up key exchanges and encryption using IPsec. So these are great little protocols. So Diffie-Hellman allows us to generate keys without having the two endpoints communicate before. So a new shared key is never actually sent between the sender and receive. They're generated on the fly. Now, as we've already said, these algorithms create keys, and with the pairing of IKE, we could share these keys over the connection in a secure manner. So how does this work? Well, if you have a look on the top one, Alice, she's agreed to use yellow with Bob. They then add the secret color, which is key index, and it creates a private color. Bob does the same thing, and as you can see, Alice came up with orange, Bob came up with green. Now, when you send back and forth between these two parties using their colors, Bob's private color with Alice's secret color comes up with a final color. When you do the same for Bob using Alice's private color with Bob's private color, you come up with the final color. So basically what we're doing is using very large numbers mashed through an algorithm to come up with different starting points, mixing them together, and spitting out the same result for both ends of the communication. Because we get to the final destination being the same, we can encrypt and decrypt messages from each other. So, welcome to the summary. So, throughout the 3 videos, sections A, B and C, we went and had a look through how security breaches can affect businesses and threaten people's privacy. We looked at the various vulnerabilities, how they can be exploited by a third party. We looked at the various attack vectors that a threat can arrive. We looked at the tools and terms used. We also had a look at common types of attacks, being eavesdropping, modification data, address spoofing, so on and so forth. We then looked at the common types of malware, being worms, viruses, and trojans. We then went through the various types of attacks, reconnaissance, access, and denial of service. And then we went through and looked at the various depths of the different attacks that can occur for access, for reconnaissance, and denial of service. We looked at the different techniques used within those different types of attacks. We looked at exploiting the inbuilt vulnerabilities within our protocols that we use for communication. That covered IP, ICMP, TCP, UDP, DNS, ARP. Then we came down to ways of having methods to protect yourselves, talking about confidentiality, integrity, and availability, and then looking at how we can use multiple devices to secure our networks in depth so that we're not just protecting the perimeter, we're protecting most of the known systems. So we then had a look at what devices can help us in securing our network. So we had a look at the fact that we have the firewalls, we have the adaptive security appliances, we have AAA servers, we have intrusion prevention systems. We had look at the protocols that allows us to protect our data, so securing the data integrity, the origin of the authentication, the confidentiality, using the hashing functions. We then looked at the 3 main known hash functions, MD5, SHA, and SHA-2. We then looked at how we can add an extra layer of security to that by using HMAC. Then we looked at our encryption being symmetrical and the algorithms that we can use for symmetrical encryption being DES, 3DES, AES, and having our guard dog go off in the background. And we can have the next level of asymmetric algorithms and use of the various algorithms in combinations to give us different outcomes. And that brings us to a very long chapter end. There's a lot of information in this module to digest. Please take your time. There's a lot of new concepts for most people here. So I strongly suggest you read through the material a couple of times and just absorb it, because it is the introduction, okay? There's a lot of new concepts and things to go through. Thank you for watching, and I'll see you in the next chapter. Bye for now.